So we were looking at indexes in the last class, and this is our final class. Somehow we managed to complete all our classes. I hope I have done some justice to all the lectures I have given. I have also shared all my video lectures with you, which was really a very tough job for me. Recording every day, editing, spent a lot of time on preparing things. I understand that there are some audio issues with some of the videos because of the noise that I've captured. But then I'll try to improve the quality somehow. Only surprising thing is I get requests from students from other classes who are not from even from my class to post lectures and materials. So that's why I continue this initiative for such a long time. Anyway, I hope that that will help you for your examinations. Please go through all the materials. Definitely, you'll be able to make it this time. Okay. So let us finish our one final concept, indexes. We also have another concept, NoSQL databases introduction. I'll post a video on that. You just go through that. So don't skip any of the concepts. So what you learned in indexes in the last class? Can you remember what all we learned with respect to indexes? We learned many things, right? We learned what are the disadvantages of not having an index. I mean, how your search time increases. And then we looked at one particular index, the primary index. And we also saw the definition of sparse index. After this, we went in and we looked at secondary index. And we said that secondary index is a type of dense index. And we have taken some problems. We have compared how the indexes reduce the number of block accesses required. Okay. Today's class we look at what is multi-level index, a very important concept. Let me directly go and show you an animation for multi-level index. Say you have 8 data blocks. How many data blocks you are going to have? Say I have 8 data blocks. So each one you are seeing here is a data block. It will hold many records. That's why I given dots here because of space constraint. So if I have 8 data blocks, I want to create a primary index for this. So if I create a primary index, let me assume that a block can hold how many records? 4 index entries. So we are going to create a primary index and our assumption is a block can hold 4 index entries. If we want to create a primary index for 8 data blocks, then how many blocks I should use for my index entry? If I have 8 data blocks and in one block I can hold 4 index entries. If I want to create a primary index, how many blocks I need for my index? 2 blocks, right? So you see here, we'll have 2 blocks to hold our index entries because for a primary index there should be a pointer to every block. So we'll have one block containing 4 values, another block containing 4 values. So you see there is a pointer to 4 blocks and this is one block. We assume that a block can hold 4 index entries. Since we have 8 data blocks, you should have another block containing another 4 pointers like this. So that becomes your primary index. Earlier what we were doing, we used to do a binary search on this index. We'll do a binary search on this index, go to that block and then we will go to the exact data block to access that record. Now in a multi-level index, what we are trying to do is just build another index for this primary index. So this is another primary index built for your index, an index on an index. So how many blocks you have here? 2 blocks. So number of entries here will be 2 entries. So here this pointer is going to point to this block and this pointer is going to point to this block. And what will be here? That will be the record value of the first record here. So that is 111 and the value of the first ordering field here 127. So this becomes a multi-level index. On an index we built another index. So like this you can go many levels. This first level, this is called the first level index, whereas this is called the second level. And here we also say this to be the top level. So what is a multi-level index? First I build a primary index. For that primary or dense index, I can again build another index. So how many levels you are going to have? It depends on the size of your indexes. Okay. So when we are going to stop our levels, first I build an index, next another index, next another index. When will this index building process stop? There is a rule for that. I'll tell you what is that rule is. We'll stop whenever your topmost level fits in one block. So you'll be just proceeding first level, second level, third level. When we'll stop, when our topmost level fits in one block. And there is an advantage for that. When you want to search an item, we'll just move the topmost level to your RAM, search for the next block, search for the next block, your search is over. Okay. So like that, you can have many levels here. It depends on the size of your levels. If my first level is of a very large size, then I'll have a second level, and for that I'll have a third level, for that I'll have a fourth level. When will I stop? Only when my topmost level is fitting in one particular block. So this is called a multi-level index. What are the uses of a multi-level index? How it reduces the number of block accesses. I have given the hard disk here, and say we have an employee table split across 3000 blocks. So these are blocks, data blocks. So how many blocks we have here? How many blocks we have here? 3000 blocks. And for this, I build a primary index, first level index. So when I build a primary index, how many entries will be there in my primary index? 3000 entries, a pointer to every block. And let's assume that each index entry is 15 bytes in length, and each number of index entries is equal to number of data blocks in a primary index. So we are going to have 3000 index entries in our primary index. The block size is 1024 bytes, and the index entry size is 15 bytes. How many entries can fit in a block? 1024 by 15. So you'll have 68 index entries in one block. So to hold 3000 index entries, how many blocks you need? I can fit 68 entries in one block. I should hold 3000 index entries. How many blocks I need? It's nothing but 3000 by 68. 3000 by 68 will give you 45 blocks. So my first level index will be built. That is, it will have a pointer to every block, and then it will be how many blocks? 45 blocks. Because every block can hold 68 index entries. Every entry will be pointing to a block. So you see here, there are pointers from the primary index to your data blocks. So if I do a binary search here, what is that binary search? It is log 45 base 2. So how many blocks I should access on an average here? When I do a binary search here, how many blocks should I access? 6. Am I correct? So you should access 6 blocks on an average to locate where that particular data block is. So I say, suppose you access this particular block and then you identify that's where the actual data record is pointing to. There is one more plus one access to go to the data record on the database and get that. So it is 6 plus 1. So you end up with 7 block accesses when you have a primary index and a 3000 block data file. Now if I built another secondary level index for this primary index, how many blocks this secondary level index is going to take? How many blocks you have for your primary index? 45. How many index entries a block can hold? 68. So this 45 can be very well accommodated in one block in your secondary level primary index. So you'll have all the 45 entries here. And this becomes your topmost level. So from this second level, you will have pointers to all the first level primary index. Okay. So you have built a multi-level index, and we have to see in what way it is advantageous. Say I want to search for some data here, 1111, some data here, that is my search query. So what I will do is, I know that this particular block is the topmost level, I load it into memory. Then I will do a search and then I will find the block which is actually pointing to this block. So this is one block access, then I go to this block and this is the second block access. From here I will go and access 111, that is the third block access. So how many block accesses? Now I come to 3 block accesses. Earlier without the secondary level index I was doing a 7 block access. So you see that there is an advantage in having a multi-level index and it reduces the number of block accesses. So I have just given that problem we have discussed as an animation in the slide. You can go through that later on. What are the problems with multi-level indexing here? Again, can you think of any problems with multi-level indexing? Say when you take a look at the multi-level index that we have built earlier, everything is ordered. This is ordered, this is ordered, this is ordered. Everything is in some kind of a sorted order. If I'm going to insert more records or more blocks, then what should happen? There should be insertions in your index entries too. If I delete the actual data blocks or data records, the index entries also should be deleted. See, I don't have an employee of ID 111. I deleted him. Should I have an index entry for him? No. If I insert a new employee and is in a new block, definitely there should be an insertion happening in your indexes. And when it is a multi-level index, you have to change all the levels. So this is one of the difficulty they had with multi-level indexing. If I change, I have to change all the indexes. And how to address that? That's where they went in for dynamic multi-level indexing. What is dynamic multi-level indexing? I'll have some additional space in every block so that when I get a new entry, I can very well go and insert it rather than moving my records or shifting my records. And dynamic multi-level indexing or indexes are implemented using tree data structures. When you talk about dynamic multi-level indexes, it is being used, it is implemented by using tree data structures, B tree or B plus trees. What are B tree or B plus trees? Special cases of a tree data structure. You all have learned tree data structure in your data structures class. I hope you are all very good in coding a tree data structure. So can you take a look at a tree data structure here? So this is a sample binary tree we are seeing. And if you want to search for the value 3, how you are going to search? Go to the root. Whatever that is less than the root will go to the left hand side. Whatever that is greater will go to the right hand side. And then here you come, whatever 3 is greater than 2, so you go here, you'll be able to locate the node. And you also know what are leaf nodes. Leaf nodes are the nodes, last nodes in the tree, they don't have any child elements. What about child nodes? They have some parent nodes. And you also have non-leaf nodes. These non-leaf nodes are also called internal nodes. What is the root node? The node on top of the tree, it is not going to have any parent element. You also know depth of a tree, right? So I have given depth of a tree using levels. This node is at level 0, level 1, level 2. So trees you should be very good at, and this is a very simple tree example. What are the disadvantages you will face when you are using a tree data structure? Just a tree data structure. I'm using a tree for all my searching activities. I built a data structure using trees for all my search. What kind of disadvantage I may face? Say based on the kind of data that is coming in, your tree can really become skewed. Skewed in the sense, say I get all the data like 8, 10, 11, 12, 13, 14, 15. So you see one side of the tree is really large and it's just like a linear search happening. Say if I want to search for 15, it's like I should be just like this linearly going through my tree. A search for 2 will be faster, whereas a search for 15 will be less, it will take more time. because it's almost resembling a linear search. Sometimes your data can cause your trees to be skewed. So how this problem is fixed? How will you fix this problem? How you fix this problem is, we'll talk about a self-balancing binary tree. No matter what kind of data comes in, what my tree will do is, it will adjust itself such that the depth of the tree is always minimum, or the height of the tree is always minimum. It will not get into a mode where it is skewed. So what will happen is, say, now for the same tree that we have seen here, it was skewed, right? When you go for a self-balancing tree, it will see to that the height of the tree remains minimum and all the leaf nodes are at a constant depth from the root. What is the advantage of maintaining a self-balancing tree? You want to search for 1, 3, 5, 7 or any of the elements, the time taken will be constant. So it's not that for one element I will get a faster search result, for another element I am going to wait for a long time. So this is a self-balancing binary tree. I mean, have you learned any self-balancing trees in your data structures like AVL trees, red-black trees, B trees, b+trees? All these kinds of trees are self-balancing trees. So as and when the tree gets created, the algorithm will adjust the tree such that the tree remains in a constant height. You understood the advantage of this? Okay. So we are going to look at a dynamic multi-level index that will use a self-balancing tree. It's not a binary tree, it's a self-balancing tree. So our objective is to use a self-balancing search tree as a dynamic multi-level index. So our index will be nothing but a self-balancing search tree. What is the advantage of such an index? The height of the tree will always be minimum. So let us go back to our primary index that we created. You remember the primary index we created for 8 blocks just now, right? So how many blocks we add here? 2 blocks. From these 2 blocks, you will have pointers to every data block. And then we created another primary index for this. That is the topmost level, and you had some pointers here. You are clear with this diagram, right? You call this to be the first level index, this to be the second level index. So this is the diagram we arrived at. Say you just rotate this diagram. When you rotate this diagram, you can see it looks like a tree. And what is this? This is the actual hard disk containing your data blocks. This is the actual hard disk containing our data blocks. So every block is there on the hard disk. It's the data blocks. Whereas whatever you are seeing here, that is your index structure. And you can see that the index structure looks like a tree, right? And you call this to be the leaf node. What is the leaf node? The last nodes in your index structure that will point to the actual data records. Or in other words, you can say that is the first level of index created for your data records. And what are the other nodes? The other nodes come on top of your leaf nodes. It can be either internal nodes or the root node. So if your first level index is very large, you'll have internal nodes and then the top level root node. Okay. So what you see here and understand here is, what is this? This node is nothing but, what is that? Block. What is this node? This node is nothing but block. So every node in your tree is nothing but a block that can be of 1024 bytes. And how many? These two things you have to remember. Every node in the block, okay, every node is a block in the tree. You all agree to that? So you say this is your tree data structure. Every node is nothing but a block. And what is your leaf node? Leaf nodes will be having values and pointers. The pointers will be pointing toward actual data records. Whereas these are called internal nodes or root nodes. These nodes will be pointing to other nodes in your tree data structure or your index. which is pointing to the data records, the leaf nodes. So we will see how to construct a index using a b+tree. For that, we have to understand certain things. We understood every node is a block in our tree, and every node holds values and pointers. So what a node holds, you have values, you have pointers. See, this pointer is called a data pointer because it's pointing to the actual data. Whereas this pointer, you can call that to be a tree pointer. Why you say that to be a tree pointer? Because it's actually pointing to other internal nodes in your index. So the only the leaf nodes will have data pointers, the other nodes will have tree pointers. Okay. So this concept alone you should have. How many keys and pointers a node can hold? How many keys and pointers a node can hold? It depends on the size of your key and the pointer plus the size of your block. Okay. So for our construction, let's assume that a block holds two key values. So how many types of nodes we have? We have leaf nodes, we have internal nodes or the child nodes, and we have a parent node. So we have to look at some properties of leaf nodes. What are the leaf nodes? That point to the actual data records. A leaf node will have a structure like this. It will have the key. Say the employee ID is 111, the pointer to that record because it's a leaf node. Key 2 can be another employee ID pointer, and we'll have a pointer next pointing to the next leaf node. So you call these things to be data pointers because they point to the actual data records on your hard disk on the blocks. Say, let me give an example here. This is one leaf node having an value 111, a pointer to that record, and then this is 112, a pointer to that record, and then this is pointer next. So let's take our DBMS. Let's assume this is our hard disk. Say we have all the records here. So you have 111. Say this is the leaf node, right? So it will be pointing to the actual records on the disk. This pointer next is actually pointing to the next leaf node, and this leaf node has two more values. Why we take only two values in a block? Because we assume the block can hold only two key values. So for holding four key values, I am using two blocks here. And you see here, this pointer is pointing to this block and this pointer is pointing to this record. So that's how your leaf nodes are. That's the organization of your leaf nodes. It's key, pointer, key, pointer. Another major property is it's in the sorted order. Say this key is less than this key is less than this key is less than this key. So it's a sorted order of lists connected together. Okay. There's one more property for your leaf node, that is every node should hold minimum p by 2 values. Minimum p by 2 values. What is that p? P represents the number of data pointers. How many data pointers you have here? 2 data pointers. So minimum how much it should hold? 2 by 2, that is equal to 1. Every leaf node should contain minimum 1 key value. How you arrive to that? Using the formula p by 2, where p is nothing but number of data pointers in your leaf node. Data pointers will exist only in your leaf node. Please have that in mind. So whenever we are constructing a tree, we should ensure that our leaf node contains at least one value in its leaf nodes. Internal nodes, what are the internal nodes? Say the leaf node is the first level index. The internal nodes are nodes coming above the leaf node, right? So internal nodes have their own properties. We have to see what are those properties. So internal node organization will be like this: pointer, key, pointer, key, and pointer. So what these pointers are? Tree pointers. An internal node will have more number of pointers than your leaf node. Say here you have a pointer, key. So this can be pointing to certain nodes, this can be pointing to certain nodes, this can be pointing to certain nodes, and you can have the key value, say 111 or 112 here. What are the properties of the internal nodes? Say if I store two key values, how many pointers I will have? 2 plus 1, that is 3. So that's what it says here. If I have k key values, the number of pointers is k plus 1, 3. That is the property of your internal node. And every internal node should have at least ceiling of p by 2 tree pointers. Say if I have an internal node, it is mandatory that this node should be pointing to at least p by 2 records or p by 2 nodes. So what is this p? Number of tree pointers. How many tree pointers you have? 3 by 2, and we talk about seal. Seal is like the upper level. So how many tree pointers every node should be pointing to? Minimum 2 tree pointers. It means an internal node should point to one record, one block this side and one block that side. That is mandatory if your number of tree pointers is 3. Only the root node is allowed to point to only 2 tree pointers. The root node will always be one node, right? It will point to only 2 tree pointers. Okay, that's all about our discussion on internal nodes. We have one more very important property for the internal nodes. That is, this pointer is actually in an internal node is pointing to all values that are less than and equal to this key 1. For instance, if I have key 1 to be 3 here, all the values pointed by this side should be like 1, 2, 3 like that. It should not be greater than 3. It should be less than equal to 3. Whereas a pointer here will be pointing to all values that are greater than 3. So it should be 4, 5 or 6. It should be greater than 3 and it should be less than equal to this value. Suppose if it is 8 here, you can have 4, 5, 6, 7, 8. So all the values are greater than 3 and less than or equal to the key 2. Whereas this pointer will be pointing to all values greater than key 2. What is that? 9, 10, 11. So this is the property of your internal node in your B plus tree. So let me attempt and somehow explain you how to create this B plus tree for the following values. Say we'll just take a set of key values and then we'll just create our index structure. We'll see the algorithm, how it works. We'll understand the algorithm using a sample from your textbook, an example from your textbook. So we'll take up all these key values and we are going to construct an index for these key values. And we'll have some assumptions here. Number of data pointers in the leaf node is 2. So order of leaf node is 2. What do you mean by data pointers in the leaf node is 2? I can have 2 keys and 2 pointers to my data records. And every leaf node should hold how many values minimum? That is number of data pointers by 2, that is 1. When you are having a leaf node, minimum number of records in the leaf node should be 1 and maximum is 2. Number of tree pointers in internal nodes. What's a tree pointer? Pointing to another internal levels. Number of tree pointers is 3. We assume that it is 3. So what is the number of values you can store? That is 3 minus 1. So if you have 2 values, number of pointers will be 3. So that's what it is. So number of key values in a node is seal of 3 by 2, that is 2. So let us go and start creating this tree. So how many values will be stored in our leaf nodes? Maximum 2, minimum 1. We'll first start creating the leaf nodes and then we'll start building our index. So let us talk about inserting 2 values in a leaf node. A leaf node can take 2 values. So you can see directly I can insert that. And this is a leaf node and this is the key and this is actually a data pointer pointing to your record on the disk. This is again a data pointer pointing to the actual record because this is a leaf node. 2 key values you can hold. Say next I'm going to insert 1. Where 1 should be inserted? The property of the leaf nodes is key should be in the sorted order. Key 1 should be less than key 2 should be less than key 3. So where 1 should be inserted? 1 should be inserted here, but you see this block is already full. So what we have to do is we come to a situation called overflow. This block is going to overflow now. So we'll go and split this block. We'll go and acquire a new block and our property changes like this. So what we are going to do here is we are going to acquire a new block. say we have acquired a new block. After acquiring the new block, if I insert, what should I be pushing from here to that new block? That is the question. If I insert, how many records from this block should move to that new block? So for that, we have a formula. That is, you take the number of data pointers in your leaf node, you add 1 to it, you divide by 2. Then you find the seal of that. So that will be nothing but 3 by 2, 1.5, so you'll get 2. So you retain 2 key values here and you push the remaining to the new block. So what I'm going to do is I'm going to retain 2 key values here and push 8 alone here. Okay, that's based on a formula they're doing that. So our 1 is also inserted. Now let us go and insert what? 7. Before inserting 7, you see here you have 2 leaf nodes. Whenever you have 2 nodes, you have to go and create a parent node for that. So how will you create a parent node for this? What you have to do is, on the left hand side, you see the maximum value. 5 is the maximum value, so you make 5 to be the parent node. So you have 2 blocks here. On the left hand side, you have 5 to be the maximum value. So 5 will be the parent node for these 2 blocks. And you see here what is being pointed this side, whatever values that are less than equal to 5 is pointed. Whereas this pointer is pointing to whatever values that are greater than 5. 8 is greater than 5. So you map the pointers accordingly. So when you go and create a parent node, whenever you have 2 nodes, you can have a parent node for that node. Okay. Next, what you have to insert? Insert 7. Where will you insert 7? You see there is a 7 should be inserted here because it should be 1, 5, 7, 8. There is a place to insert 7. So you can go and very well insert 7. So 1, 5, 7, 8. Is there any change to your root node? No, because this is pointing to anything less than equal to 5. This is pointing to everything greater than 5. What is the next value you have to insert? 3. Where will you insert 3? 3 should come here because it should be 1, 3 and 5. The node is already full. So when the node is full, what you have to do? It's an overflow condition, right? So what you have to do is you have to acquire a new block and split that node. When you split that node, what will happen? You'll acquire a new block like this, see? And then you'll retain 2 values here, push the remaining values here using the formula we discussed. When you insert 3 here, what happens? An overflow happens in this block, so you're going to acquire a new block. And you're going to retain 2 values here, push the remaining values to the new block. So how many blocks you have as a leaf node? 3 blocks. And then you're going to change your parent. How the parent changes? Now you have 3 blocks, right? Leaf nodes. You see here, whatever that is less than or equal to 3 is being pointed this side. Whatever that is greater than 3, 5 is pointed this side. So this is greater than 3 and less than equal to key 2. Whatever that is greater than 5 is being pointed. Since you have an additional block coming in, your parent nodes also will change because you should have the pointers to the data nodes. Another way to say this is, let me again say this. Another way to say this is, I have 2 nodes, I should have a parent node for this. What is the maximum value here? 3, I give 3 here. I have 2 nodes, I need a parent node for this. What is the maximum value to the left hand side? 5, I give 5 here. So when you're going for a parent node, just take a look at the left hand side of the tree. Whichever node is having the maximum value, make that value as the parent node's value. And you should have a parent node for every 2 nodes. Now next, what value should you insert? 12. Where will you insert 12? 12 should be inserted here. This is already full. So what you're going to do is you're going to acquire a new block like this, and then you're going to insert 12 here, and this will be a pointer to the actual data record. But what happens, this node is without any parent. You're trying to map this pointer to your existing parent node, but then you see here this node, all the pointers are busy, it's already full. So what should happen is you should acquire a new block here too. So when you acquire a new block there, what will happen? You'll get something like this initially 3, 5, and you're pushing 8 to that new block. And here you have two internal nodes. For this node, you go and create a parent. How will you create a parent? You create a parent node, you make 5 to be the root node. But then what you're going to see here is whenever you are having internal nodes, you're not going to replicate it. So you'll not replicate it. Only for your data nodes, you'll have a replication. 3 is here, 3 is here. Whereas for this, you'll not have a replication. Okay. So your tree adjusts accordingly. Okay. So like that, you keep on inserting. Say if you want to insert 9, where you're going to insert 9? 9 will be inserted here. So you see here 9 getting inserted there. If you want to insert 6, the last element, where you're going to insert it. So you go and see an insert happens. And then the tree revises itself. I know it may be a very tough thing to understand it in the very first attempt. I'll share these slides. The only thing you have to understand is whenever there is an overflow happening, you have to split, acquire a new block. Whenever you are splitting, you're getting multiple nodes, you have to create a parent node for that. See, whenever you are having a root node, this node value will not be replicated in the child nodes. Again, this node value will not be replicated in another child node of a tree that is not a leaf node. Only a replication will happen. Replication is duplication will happen when you are having the leaf node and a internal node. So that's how the tree gets constructed. But you see here at all times when we are inserting, the depth of the tree was constant. Either I want to access employee with SSN 12 or I want to access employee with SSN 1, the search time is going to be constant. Because it's going to go here, search for someone who is having an employee ID 1. So it's less than 5, it will come here. It's less than 3, it will go here and search. If it's going to search for employee ID 12, it's going to come here, greater than 5, greater than 8. So it's going to search. The height of the tree is kept at a minimum for all insertions. That is a self-balancing tree. We'll see deleting a node and then we'll stop. Say I consider this tree and then I want to delete a particular node. Say if I delete 5, what will happen? This node will be deleted. This 5 will be deleted. So you're going to not have any problem because this node still satisfies the condition that every node should hold minimum 1 value. Satisfies the formula. Say if I go and delete 12. If I delete 12, what will happen? This 12 is also deleted, so you're going to have a block even without one particular entry. So it's defying our formula. The 12 is deleted. Now your tree gets adjusted such that the records are distributed. That is, here you had 8 and 9, right? Now 9 got distributed here, and then the tree gets adjusted. So whenever an underflow happens, the records will be distributed. If I'm going to delete 9 here, then there is nothing to distribute. So you have to merge and then your tree gets changed like this. Okay. So anyway, I will put this slides. You just go through that and understand how to construct a tree. Only what we understand why we are deleting is when you delete and you find that you don't have even one entry, you see the next block is distributed. Even if the next block is just having one entry, what you're going to do? You're going to just merge and change entry. Okay. Fine. That's all about b+trees. Thank you.